Now all have turned off your mobile phones, so I'm pleased to announce our final speaker, Olivier Lévêque, Optimal Cooperation in Large Wireless Networks.
Okay, thanks for the introduction. So, since I'm the last speaker of this workshop, I would like to take this opportunity to thank the speaker for, thanks the organizers. Thanks the organizers for organizing this. I think it was a really nice workshop. It still is, I hope. Yeah, I think especially the idea to bring people from different communities together is really good, I think. So, but nevertheless, I was a bit worried this week, listening to more and more talks, then I should have something in my talk about percolation. And, well, actually I don't have anything to say a priori about percolation, so I did a small study of the percolation of the workshop itself. So if you place the talks on the regular grid, where on the horizontal axis you have the days, and on the vertical axis you have the approximate times where their talks were given. And now the rule is keep an edge alive if there is a close connection between any two neighboring talks. And so what do you get here? Well, you get a percolation cluster. And the good news is that you still get an infinite component, a giant component. Okay, and actually it matches the theory, because if you compute the empirical probability of survival of an edge, it's 0.5416, which is above the half threshold that is the critical threshold for giant components. Okay, now the slightly worse news for me is that, as you spot, I'm not quite in the giant component. And also I'm in the bottom right corner, which means that you've already listened to all the other talks and you're probably quite tired. So I'm going to try to make my talk as few technical as possible and as most descriptive as possible. Okay, so going back to the talk. So first of all, I would like to mention that this is joint work with Eifers Gur and David Shea, and it's about optimal cooperation in large wireless network. So what is the problem I'm looking at? So I'll start by describing what is my network model. So I'm considering, like Bartek, the preceding hour, a completely wireless network when there is no infrastructure that is here to help relaying communications. I have a certain number of nodes that are uniformly distributed in some area and wish to establish communication in some way. And so this is what is called, the jargon is called ad hoc wireless network. So the spatial model I have for my network is therefore a very simple one. I'm first looking at, so the nodes are independently and uniformly distributed in a square area A, and I have n of these nodes. Second, I'm considering also a uniform traffic. That is, I'm looking at the scenario, this called unicast scenario, where there are other n pairs of nodes that want to communicate together. So n source destination pairs. So this guy wants to communicate to this one to this one, and so on. Of course, so this is and the choice of the source destination pairs does not depend on the relative position. So it's completely uniform traffic pattern, no preferential attachment law, like communicating first to your nearest neighbor, nothing. And okay, so what I'm claiming here is that even for this very simple geometry and very simple traffic pattern, there are very interesting questions that needs to be solved. Somehow it goes kind of in the orthogonal direction to stochastic geometry problem here, because here the stochastic geometry is the simplest you can think of. And among which questions is the following one, which is, what is the maximum throughput scaling that you can get in such a network? Okay, so I should first define what I mean by throughput. So there are two possible versions of what you call throughput in a network. There is one which is, and there is a one-to-one correspondence between the two. I'm going to talk about the two, so let me introduce the two one after the other. There is what is called the per node throughput. So the per node throughput is the maximum rate, data rate that you can have for each communicating pair in the network. How many bits can you transfer per second from each source to each destination? And that's my per node throughput. And I can also talk about aggregate throughput, which is simply the total flow of information that you have in the network, which is, and there is a one-to-one correspondence between the throughput, this aggregate throughput and the per node throughput, which is simply the aggregate throughput is the number of communications times the per node throughput. Okay, so as you know, probably, I mean, if you've heard something about information theory, if you give me a given network of a certain number of nodes and a given area and a given setup, and you ask me what is the maximum throughput, this is a very hard problem. This is our holy grail of network information theory, that what you would like to, if you want to compute what is the maximum data rate that you can get, even for when you have 3 or 4 nodes, you're not able to do that. So for n nodes, forget it, you're never going to get to there. But what saves us is that we twist a little the question, rather than finding what is the maximum throughput of the network, to what is the maximum throughput scaling. That is, how do these two quantities scale when the number of nodes in the network grows large? And this question was first formulated by in the original work of Gupta and Kumar in 2000. And you will see that, I mean, it's a very interesting question because it leads to a quite interesting, there are many answers to this question, and I'm going to review some of them during the talk. Okay. So now, of course, I should make a comment here that in order to get any information, in order to get these n source destination pairs to communicate to each other, you need some scheduling, right? Because it's impossible that everybody communicates at the same time to its destination because of the interference that you create between the networks. Some lines are crossing. So now we are going to try to find two things. First of all, schemes that achieve a certain scaling of the throughput. And second, we are trying to find whether these schemes achieve the optimal performance. Can we get optimal, do the schemes that we design achieve the optimal performance in such networks, in the sense that the scaling is order optimal. So before I move to trying to answer this question, let me define what is my communication model. So my communication model is a quite simple one and widely acknowledged in the community of wireless networks. That is, if you have a signal, a set of nodes that transmit signals xk, each of them transmit a signal, different signal xk, then what you receive at another node I is a signal yi, which is a weighted sum of the transmitted signal times some attenuation factor hik, which are called the fading coefficients. In addition, since you're transmitting signals over the air, there is some background noise, which is called zi, which we call zi. And we model this noise as being additive. And well, so this is a widely acknowledged model for communications. Let me specify here that we assume that each node has a power P in order to transmit. And for simplicity, we are going to assume that the noise is unit power. So we just take power 1 for the noise at each node. Okay, so now the controversy goes more into what model do you take for your channel fading coefficients. So there are quite a lot of number of models for this. I'm going to consider the following one, which is motivated by physics, by Maxwell's equation. And it's the free space propagation model. So it says that the fading between node I and node K can be represented as some constant divided by the distance between the two nodes. So it's inversely proportional to the distance, and multiplied by a phase shift, which is also proportional to the distance measured in carrier wavelength units. So if you communicate at a given wavelength, that's going to represent your phase shift over your phase shift between node I and node K. Okay, so as I said, it's not the only model that exists in the literature, but as it turns out that this model is the one that finally will have everybody agree on at some point. Okay. Yes, please?
What's J there? Is that
so J is a constant. It's the Fries constant. It's just a constant. It won't play any role in what it can be. It's going to be something. It's some universal constant that doesn't depend on the placement of nodes or anything.
Then 2 pi doesn't matter.
Yes, true. Yeah, indeed. I could have removed the 2 pi.
No, he was asking about J, not G.
Ah, J. Sorry. J is for engineers the square root of -1. Okay.
What about ground reflection? Usually people would
No. Yeah. So.
It's a complex number.
Yeah. J is
I.
I. Okay. Very frustrating for me. I graduated in math, and now I ask the question, what is your J here? Okay, sorry about that.
Then HIK can be complex?
Yes, indeed. So yes, the signals are usually modeled as complex because of the phase component of the signals. That's also widely accepted. So if the X is complex, the Z are complex. Okay, and as François was going to ask, this is the free space propagation model where we assume that there is no scatterers along the way, so there is no reflections of the signals. If you want to take into account signal reflections, what people traditionally do is they replace this 1 over r here by 1 over r to the alpha over 2, where alpha is called the path loss exponent, taking into account for faster decay of signals over distance. For simplicity, I'll stick to the free space propagation model where alpha equals 2, but I'll mention also what changes if we shift to other propagation model. Okay, so now with this communication model, let me review what have been the different results in the literature. And I'm going to give a very non-exhaustive list and strongly biased also. So please do not feel offended if your name is not there, because it's really a short list. There are many papers with many different assumptions, and so I don't want to offend anybody. So there are basically two sets of results in the literature about the throughput scaling of wireless network. One set of results are results that deal with new communication schemes. So the new schemes that allow to achieve a better throughput scaling. You know, that there is a sequence of papers that have proposed new schemes that achieve better and better scaling. And there is another set of results which are called information theoretic limits, where now you don't ask for a new scheme, you just want to show that whatever the scheme you use, you're not going to do better than this or that scaling. And as a matter of fact, there is something kind of surprising here, that these two sets of results have been obtained usually obtained in two different setups. New communication schemes have first been designed for what is now called dense networks in the literature. So what is a dense network? It's what you would imagine. You have an increasing number of nodes inside the fixed area. And you have a fixed power per node, also P. And you have an increasing number of nodes. So as the size of the network, or as the number of nodes increase, the network becomes more and more packed with more and more nodes inside. In the extended scenario, you have an increasing number of nodes, but now the area scales linearly with the number of nodes. So the density of nodes in the network remains constant. And also you keep a fixed power per node P. And now, okay, of course the question you can ask, what is the most appropriate model for reality? So I claim that none of these is the appropriate model. I'm going to make a point about this right after this. But it's kind of strange that somehow in one setup, people felt like, aha, we can build new schemes that will do better than the previous ones. And the other setup, people felt like, okay, now in this case, I want to prove that we cannot do better than what has been done before. There is not a one-to-one correspondence between complete one-to-one correspondence between these two and these two, but still, as you will see, so I'll refer to some papers now. So the first work, as I already mentioned, is the one from Gupta and Kumar in 2000, where they came up with a scheme called multi-hop communication, where they showed that using this scheme that I'm going to describe in a minute, you can get significant throughput. And they had a way to show that actually, if you make some assumption on the way networks, wireless networks are operated with the current technology, their scheme was order optimal, or very close to order optimal. There was a log n factor missing. So this gap was next closed by Dus, Franceschetti, Tiro, and Say in 2005, where they showed that actually using percolation theory, now it comes again, I can talk about percolation, you could close the gap and show that the scheme, a modification of the scheme originally proposed by Gupta and Kumar was order optimal. Order optimal in the sense, if you always make this assumption that there is no, you cannot go beyond actual technology for wireless networks. But then two other papers, starting with the work of Aaron, Saligrama, and our work afterwards, the same year, showed that actually you can go beyond the limit that was first shown in Gupta Kumar by, if you agree to modify how you operate the network at the very low level, at the lowest layer called the physical layer in networking. So if you accept to modify how the chips operate, you can actually potentially, theoretically, get much better throughput scaling. And I'm also going to describe this result carefully. On the other hand, there has been a series of papers trying to prove that you cannot do better. Actually, the first paper, the first idea of these papers that was initiated by Kumar and Xie in 2004, they had a sequence of two papers, 2004, 2006, about this. The idea there was on the opposite, to show that actually the result of Gupta Kumar, which was optimal in making some assumptions on the way communications is handled, was actually optimal in a much more general context. In an information theoretic context, you couldn't beat this throughput scaling. And so there has been quite a series of attempts to prove that Gupta Kumar strategy was the optimal one until 2006, 2004, 2005. But none of these papers was completely successful until last year. Franceschetti, Migliore, and Minero proposed a new approach to the problem, and were kind of showing that actually the scheme, the original multi-hop scheme proposed by Gupta and Kumar was optimal based on a very reasonable argument. Okay, so it seems there is some contradiction here, because now these people are saying that this is the best thing that you can do, but these people are at the same time saying that no, you can do better. So, okay, these are two different setups, but we are going to see that we are going to try to solve the contradiction. So the claim I want to make here is that actually the way to resolve the contradiction between these information theoretic limits and these achievable schemes on the other side is to quit the idea of looking at particular regimes for wireless networks, so either extended network regime or dense network regime. So the first claim I want to make is that there is not one universal scaling law in wireless network. So you're not going to find one throughput scaling like square root of n or whatever. Depending on what are the network parameters, you might find different answers. So, and if you go back to these two setups have this bad thing that they couple the network parameters. Here A is increasing with n, here A is fixed. And actually what I'm arguing here is that these three parameters that I was mentioning in the previous slides, number of nodes, power, area, should be treated as independent parameters. And depending on, so it doesn't mean that if you want to establish a scaling law result, you should still have like for example, P is for the order n to the gamma, and A is of the order n to the beta, but you shouldn't fix what beta and gamma is. Depending on the values of beta and gamma, you'll get different answers. So the program for today is the following. I first would like to characterize the maximum throughput scaling of the network when, first of all, n grows large. Okay, I'm always going to consider this situation, that n grows large, because I'm talking about scaling low. That's the only thing we can hope for. And there is no power nor space limitation. So you're in a network where the number of nodes increase, but there is no, you have as much power as you want, as much area, as much space as you want. Second, I'm going to study the same question, but now n grows large, area is as large as we want, but there is power limitation. So you have, each node has a power which is, which might be limiting the communication rates that you can get. And third scenario is I want to study when n grows large, you have as much power as you want, but now you're limited in area. The area of the network is not as large as you want. So perhaps here I should make a comment. It seems at first that area, for people in, that have worked on connectivity or wireless network, it might seem at first that area is a limiting factor when it's big for connectivity issues, right? When you have a network which is too spread, some nodes might lose connectivity with their pairs. And therefore, it seems at first that area is the limiting, big area is limiting the throughput of the network. Somehow, for me, this I classify into the power limitation case. When you have a big area, that's when you lack power to transmit to the nearest neighbor or to the people who are further. So, but as you will see, area is not. So area is not so much a limiting factor when it's too large. If you have enough power, you can take this. You can deal with that. But it might become a space limitation if it's too small, because in this case, the number of independent streams of information that can flow in the air can be not enough. And I'll explain this. I'll explain this in a minute. Okay, so let's start with the first point. We grow the number of nodes, and in the case where there is no power or space limitation. So here, there is already a question. As you increase the number of nodes, you have more and more communications to relay. And this, a priori, could be a very limiting factor, because you have more and more communications to relay, so the fact that you have more and more nodes in the network can simply be the limiting factor. That's what was supposed or proved with the state-of-the-art, the assumption on the state-of-the-art wireless communications in the paper of Gupta-Kumara, by the way. So we are going to see here that the answer to this question is no. But first, let me go through the various schemes that you can think of in order to combat this fact that you have to relay many communications at the same time. So the first scheme, the simplest one that you can think of, is time division, which means, okay, you have all these n communications that needs to be established in the network. What do? You communicate one at a time. So first this guy transmits, then this other guy transmits, and so on. Okay, fine. But here, how many bits are you transmitting per second? Well, when you're transmitting a constant number of bits per second at the rate that you have. If you don't have power limitation, fine, you will be able to transmit a certain number of bits. But then you have to wait order n time instance until you transmit again, right? Because everybody takes turn transmitting. So because of that, your throughput, your per node throughput, so the data rate that you get for one communication is order 1 over n. Because as n grows large, you have more and more nodes communicating, more and more source-destination pairs communicating, so the data rate is order 1 over n. Okay, not so good. The second thing is the multi-hop scheme proposed by Gupta and Kumar. So Gupta and Kumar in 2000 showed the following thing, that actually you can, of course, you cannot have order n simultaneous communication, of course. It seems that if you treat the other communications as as noise, you won't be able to have other n communications that cross the network at the same time. But what is doable is to have other n local simultaneous communications. Like these two guys can communicate, assuming that the interference created by these is not too much. And if this interference is too much, then you can perhaps have these remain silent and communicate one time onto each other. So basically you can show that you can have other n local communications. This is called now spatial reuse. And the thing is that, of course, this is good, but the price to pay for this is that if you want to go from one node to the other one, from the source to the destination, sorry, you'll have to go through many hops before getting to the final destination. And that will typically take a number of hops, which is of the order of the diameter of the network, which is of the order of square root of n. But this is already much better than the previous scheme, because now you have only to wait square root of n time slots before transmitting to your destination, and therefore the throughput has increased by a large factor, which is 1 over square root of n. Still, it's not constant with the number of nodes, so still as you add more and more nodes in the network, you cannot, you have a rate that decreases to 0. Okay, so now I would like to introduce what is our scheme, what we propose, and our scheme will allow actually to beat this limitation. And in order to do this, I need to introduce the concept of MIMO transmission. So MIMO is the acronym for multiple input, multiple output systems. So, and in the context of network, you can think of it as the following. You have a cluster, let's say you have a cluster here of m nodes that wish to transmit information to these other cluster of m nodes. So if you assume that you have a centralized processor on each side that says to every node what this one is transmitting and what signal it is transmitting, and here you have a centralized processor that processes all the incoming data, then you can show that actually if you have m nodes on each side and there is no power or space limitation, that's crucial here, then you can transfer m bits simultaneously via this system. So you can transfer, instead of transmitting, when you have this multi-hop communication, you transfer 1 bit at a time for each communication. Here, you could potentially transfer m bits. But what is the problem? The problem is that in a network, you don't have a centralized processor on each side. Nodes are placed at different places. And so in order to obtain this transfer of this reliable transfer of m bits, you first need a dissemination phase at the transmit cluster where every node is going to say to every other node what he wants to transmit to its destination. And here at the receive cluster, you'll need an aggregation phase where you receive some information and you forward it to the destination that was needing this information. So this somehow prevents you from transmitting indeed m bits reliably at once in a network. Nevertheless, this is at the heart of the scheme that we propose. And notice that this needs, so in order for this to work, you need to assume that each node is able to receive many signals at the same time. And this is the assumption, this is to superpose all the received signal at the same time. And this is somehow the assumption that is not yet implemented in actual wireless networks. So this requires, this is the modification of the physical layer. Okay, so now let's try to apply this idea to our network. And that's the hierarchical, what we call hierarchical cooperation scheme. So we have our network, that we are going to divide into clusters. Let's say each cluster having a certain number of nodes, be the same or approximately the same. And we are going to divide the communication into 3 phases. In the first phase, the nodes exchange local information inside each cluster. And this is done with, however, you do it as you want. You exchange information inside the cluster. In a second phase, you perform these MIMO transmissions between different clusters. So if, let's say, a source here has some information to transmit to a destination which is in this cluster, you're going to have a MIMO transmission that sends this information to the received cluster. And in the third phase, so you do this taking turns. So now these MIMO transmission, you cannot do them concurrently. You have to take turns. And in the third phase, you do the same thing as you were doing in the first phase, or the reverse of the thing that you were doing in the first phase. So you forward the received signals to the appropriate destination so that the destination can decode what was sent by the corresponding source. Well, this is already something, but this doesn't allow you to do better than previous strategies. If you want the scheme to work efficiently at the network level, what you should do now is to perform a recursion. That is, I told you, use your favorite scheme to exchange information locally inside a cluster, inside this cluster in parallel. So inside each cluster now, what you can do is divide further this cluster into subclusters and do the same thing that you were doing at the network-wide level. So inside each cluster now, you're going to repeat the same thing. And once you've done this once, you can do it as many times as you want. And so you're going to have a hierarchical scheme with at the basis, very simple communication schemes inside very small clusters. And as you go higher and higher in the hierarchy, you have a more and more fancy scheme, communication scheme. And at the top level, you have communications, MIMO transmissions, which operate basically at the network level, at the level of the diameter of the network, so over distances which are of the order of the diameter of the network. And the good news is the following, that if you do this H-level scheme, the per node throughput becomes of the order of n to the minus 1 over h plus 1. So think of h being 0, so that's simply time division. That's going to give you all 1 over n, like time division. If h is 1, after one level, you get n to the minus 1 over 2. So that's as much as multi-hop. But it's not better than multi-hop. Now if you go above this, if you take h, which is 2, you get n to the 1/3, and so on. And you can get arbitrarily close to order 1 with this scheme. And at the last level, if you get very close to order 1, if you use many levels, then at the last level, you have clusters of nodes which are basically of the size of the network itself. So you have really MIMO transmission, network-wide MIMO transmission in the cluster. Clusters are very big. Actually, the clusters are exactly of the order n times this, so very close to order n. Okay, so this is a kind of vague description. Of course, you have to go more into the detail of the scheme to understand it fully, but I don't want to go too much into the math here, so just want to give you an idea of what it is. So, yes, please.
For the second phase, the transmission, don't you have interference a lot? How can you transfer together, across the network?
So that's the magic of these MIMO transmissions.
Okay,
so you transmit M signals from M nodes, M independent signals, and each node in the destination clusters this YI collects all the information that has been transferred from the M nodes, adds them up. So of course, each node cannot do anything with the information. Each node individually cannot do anything with the received information. But now the node that received the information is going to share information with the other ones. Okay. And once you have the information received by all the other nodes in the cluster, you can get to other M bits.
Everybody receives some noise, but they pass information around, and so that each one can recover perfectly.
Exactly, okay. Exactly, and then you can recover all the X's that were sent from all the Y's that you have.
So is this an assumption, ideal assumption, or something that can be achieved?
Sorry?
Is this assumption basically it's an assumption for analysis, or something that system can be built that this can be achieved?
Yeah, okay, so now there are the question, there is this restriction that I'm assuming there is no power neither space limitation. And well, of course, Yeah, so this is, it can be achieved under some assumption, yes. So this is a good point. I'm going to explain what happens in the general case. Okay, so the first conclusion to draw from this scheme is that indeed, you can, in a network with a large number of nodes, you can sustain a throughput, a per node throughput, which is arbitrarily close to order 1, provided there is neither space nor power limitation. So this is good news. Of course, it's quite of a theoretical result, because you have to imagine what does it represent to have network-wide synchronized MIMO transmission in a network of 1,000 nodes. But okay, we are talking about information theory here. So, and it gives at least hope that perhaps you can do with 2 levels of the scheme. Perhaps you can do better than multi-hop still, right? So with 2 levels, I show here that this is of order n to the 1/3, which is better than 1 over square root of n. So okay. Now, other questions more questions? Okay, so now I would like to move to the second question, which is what's happening now if there is power limitation? So you look at the same scenario, the number of nodes grows, the area is as large as you want, but you're limited in power. So the question now is, will this hierarchical cooperation scheme still outperform multi-hop? And this is not clear. Why is it not clear? Let me first try to see the 2 schemes, how much power they require each of them in order to work. So the first scheme, if you want the multi-hop scheme to work, you should have that the SNR, so the signal-to-noise ratio that you get for every hop that you do, is greater than order 1. So which in the engineering jargon means is written more like is greater than 0 dB. And what is the SNR between 2 nearby nodes? Well, it's the power of your node divided by 1, which is the noise power, divided, given the model that we have for the attenuation of a distance, it's further divided by d squared, where d squared is the average distance between nearby nodes. So if you have this SNR, which is greater than 0 dB, you can achieve multi-hop. You can get to order 1 over square root of n with multi-hop schemes. What happens now with hierarchical cooperation? A priori, well, in hierarchical cooperation, you need these long-range MIMO transmissions. So you're going to need to have communications over distances which are much longer than multi-hop, that single hops, right? You basically, at the highest level, you need to have communications which are of the order of the diameter of the network. And the diameter of the network, it's a simple thing to see that it's approximately of the same order as square root of n times the distance between any 2 nearby nodes. Therefore, it seems that you're going to lose here. The thing is, when you do MIMO communication, so MIMO communication not only allows you to transmit order m bits at once, but it also gives you a power gain, because the signal that you receive at node I is the sum of all the signals that have been transmitted by the transmit nodes, right? And the sum, therefore the total power of the signal that you receive at one node is amplified by another n, by a factor n. And this compensates for the fact that you're transmitting over longer distances. So in total, the condition that you have in order to get the hierarchical MIMO scheme to work is the same condition as for multi-hop. So conclusion, you will get a throughput, per node throughput in this case, we still get a throughput which is arbitrarily close to order 1. We could ask the next question is, what if now the power falls below this? So now if you have really an SNR which is much smaller than 0 dB, so the power per node is really decaying with the number of nodes. So now the question is, well, you don't have enough power, so you cannot use the same scheme as before. You're limited. And a simple solution seems there to do bursty transmission. What do I mean by this? is that before you transmit anything, so you don't have enough power, but we are assuming here that you have an average power constraint. Over a certain number of time slots, you have a certain power budget. So what do you do? Instead of trying to transmitting at each time slot, you just wait for a sequence of time slots which is of the order of 1 over SNR, and at the final time slot, you just transmit with an increased order SNR power. And this allows you to overcome the power limitation. But of course, since you're waiting for some time, not transmitting anything, you're losing in throughput, like in the time division scheme. In the time division scheme, when one node was first transmitting at a constant rate, but then had to wait that all the other nodes wait. And here, you will lose in throughput for the same reason. And you can show that in this regime, the optimal per node throughput can be arbitrarily close to order of SNR, but now SNR is much smaller than order 1. So you don't get to order 1 throughput in this case. But this is still achieved by hierarchical cooperation. So it's still better to use hierarchical cooperation in this regime than multi-hop. So conclusion number 2, when there is power limitation but no space limitation, hierarchical cooperation achieves the optimal throughput scaling. And if you have enough power, you can get arbitrarily close to order 1 on the per node throughput. If not, then you get to this order SNR. Okay, I use these two definitions of throughput now. So I was so far focusing on the per node throughput, how much throughput you can get per communication pair. Now I want to shift, just for readability reasons, to aggregate throughput. So what is the maximal flow of information that you can have in the network? So as I told you, the aggregate throughput is simply n times the per node throughput. So if I rephrase this statement for aggregate throughut, this is saying that as soon as you have the same amount of power, this SNR is greater than 0 dB, then the throughput T of n can be arbitrarily close to order n. So it can scale arbitrarily close to linear in the number of nodes. And here I want to mention something about the case. So this was everything was assuming this free space propagation model, but so it seems that hierarchical cooperation always wins on multi-hop. But actually, if the power path loss exponent alpha turns out to be greater than 2, then you get a completely different story. And we have a paper on this I mean, there are very interesting things happening here, but just not to, I don't want to deal with all this, so I just skip that. And in this case, there are regimes where multi-hop is the optimal scheme. And there are also regimes where neither hierarchical cooperation nor multi-hop is the optimal scheme. Okay, so but since this is a workshop on spatial network model, I thought I would spend some time on space limitation. So now we're asking, we have a network with an increasing number of nodes. There is no power limitation, so you can have as much power as you want, but the area of the network is limited. And so the number of independent streams of bit that you can transfer over the air will be limited. And therefore, you'll get some degradation in the throughput. So the question here is the same as before. In this context, who is winning? Hierarchical cooperation or multi-hop? So this was the result. So the first people to have shown this spatial limitation are Franceschetti, Migliore, and Minero last year, 2009. And, well, they formulated the result as it is written here, focusing on the extended network case, so where you have a per node throughput P, an area, a number of nodes increasing, and an area linear with the number of nodes. They showed that you cannot get, so the aggregate throughput cannot be better than square root of n, which translates into the per node throughput result into R of n is at most of the order of 1 over square root of n. So their conclusion from this result was multi-hop is optimal in wireless network, no question, this is the end of the story. So we have a quite different point of view on this. And actually, if you rephrase their result in the context of when you now let the area and power and the number of nodes scale differently, you get this more refined result, which is saying the following. If the square root of the area, so now lambda comes back. Lambda is, remember, this carry wavelengths that was in the phase shift of our signal. This is, so square root of A, so lambda is in meters, square root of A is also in meters, so this is a dimensionless quantity. So if you compute this dimensionless quantity and compare it to square root of n, so which is basically saying here that the area is of order n or less, then the throughput T of n is at most of the order square root of n. So this is the case where this formula applies somehow. But now if you allow for a larger area than order n, so basically if you allow for an area which oscillates between order n and order n squared, so square root of A between square root of n and n, then you can show, then what they say is that the optimal throughput, whatever you do, is going to be limited by square root of A over lambda. So this is now greater than square root of n. And if you go even further, so if the area scales more than n squared, then you can even get to order n. Well, the limitation does not say anything in this case. The limitation is the obvious bound that you cannot go beyond. An aggregate throughput cannot be better than order n. Okay, this sounds perhaps like unrealistic to you to have an area which is of the order of the square of the number of nodes. I will come to an example at the end of the talk trying to convince you that this is not such an irrealistic assumption. Okay, so let me now given, so these are upper bounds, right? Upper bound on the aggregate throughput. And we know some schemes that achieve some results. So this seems to say the following. This actually says the following. This is our topernary conclusion. If the area is really small, of less than n, then actually multi-hop is the optimal strategy to adopt for wireless network. And the optimal throughput scaling is of order square root of n. So the original paper of Gupta and Kumar does the best thing. On the other hand, if area is much larger, then hierarchical cooperation can achieve an aggregate throughput scaling of order n. And now there is the question, what happens between the two? Because hierarchical cooperation was not dealing with area limitations, so what happens in the intermediary regime, where area is not, square root of A is not greater than n and not smaller than square root of n? And what we showed recently is the following, that in this intermediary regime, assuming that you have enough power, as I said, I'm not considering that there is power limitation here, then in this regime you can achieve as close as you want to this upper bound that was shown by Franceschetti and others. So I should mention before going on that this result has been obtained independently by Li and Chung about the same time. It's going to be presented in ISIT 2010. Okay, so let me shortly, since I still have 10 minutes, right? I just want to give you a proof ID how to deal with this spatial limitation and why we can still do better than multi-hop when there is spatial limitation. So first of all, where is the problem? So where does the spatial limitation limit the performance of our hierarchical cooperation scheme? So as you can guess, it limits the performance of our scheme whenever we do these distributed MIMO transmissions. Because ideally, when you have two clusters of M nodes, then as I said, these MIMO transmissions allow to transfer order M bits at once from one side of the network to the other. But whenever there is spatial limitation, then you can show that the maximum number of independent streams that you can create between the two clusters is of order square root of A over lambda. So if square root of A over lambda is less than m, well, you reduce the number of bit streams that can travel from one side of the network to the other. And if you get, if in our scheme, remember, we have communications between clusters which are far away from each other. So when you let the cluster to be, the clusters are still of the same size, but are further and further away, then this is even worse. This might even get worse. And actually, it does get worse. But our result shows that actually it's not that bad. And if the distance, if D, capital D, is the distance between the two clusters, and D is of the order of square root of A, the square root of the areas, then we can show that order A over lambda D bits can be transmitted simultaneously. So we can still achieve some transmission rate between the two clusters. And that's good news because when the area of the cluster, when the distance, so at the highest level of the hierarchical scheme, the typical distance between two so the size of the clusters is of the order of the size of the network, so A is of the order of n, and the distance is of the order of square root of n. So it's exactly the case where D is of the order of square root of A. And in this case, you show that actually the outer bound that was shown by Franceschetti and others can actually be achieved. And there is another thing which is not completely obvious at first sight. If you want so this is not, this is not enough to prove that you can actually achieve that the whole scheme works. If you want the whole scheme to work, you have also to reduce the number of nodes that participate to the communications between the clusters. So if you have other M nodes participating in a MIMO transmission where the number of independent bits that can travel through the network is less than M, actually this is not good for the overall scheme. What you should do is reduce the number of nodes participating to the communication so that the number of nodes matches exactly the spatial limitation. And you should reduce this number of nodes in a way so that the total area occupied by the node is still of the same order as before. And okay, and if you put everything together, you show that the total throughput, aggregate throughput is of the order of square root of A over lambda is achievable in the network and has been shown to be optimal by Franceschetti. So we have the matching lower bound and outer bound. So conclusion number 3, when there is spatial limitation, then if the area is really small, multi-hop is optimal. But if area is slightly greater than n, then hierarchical cooperation is optimal, provided that you have enough power. Okay, so just to finish this talk, as I said before, well, okay, now if you give me a network, that was the initial goal, right? You give me a network, you tell me, okay, I have this number of nodes, this area, this power, and what will be the best scheme that I should use? So of course, we don't have a precise answer to this. That would be answering the network information theory problem. But we have an approximate answer through this scaling law approach. And it tells you that if you compute these numbers, then you can check in which regime you are and what is the optimal thing to do. So let me give an example that gives me the opportunity to show a building that was recently built at EPFL, which is kind of a fancy building, called it's a library actually. And why do I take this building? Because it's a rectangle, so easy computable area. So you have, well, so this is, you know, there are restaurants, there are lots of things in there, and so many people go to work for meetings and all this. So at peak hours, you probably have something like 1,000 students in the building. And the area, well, the building is roughly 100 meters times 200 meters. So if you discard the problem that you have holes there, the area is about 20,000 square meters. Okay, and now I'm imagining that somebody sets up a wireless network in this building, and how much throughput can one get? So if you use standard mobile phones, typically the carrier frequency of a mobile phone is of the order of 3 gigahertz. If you translate this into carrier wavelengths, this tells you that lambda is 0.1 meter. So now I'm asking, in this scenario, is there area, or is there either space or power limitation? So if you compute the numbers that I had before, if the square root of A is around 140, divided by lambda, that makes 1,400, greater than n. So as I told you, it's not so unlikely that the square root of the area, that the area is of order n squared, if you take a particular example like this. So actually, in this case, there is no spatial limitation. And in terms of power, it's the same thing, because the typical distance between any two students in the network will be of order of 4 meters. And of course, I mean, you know that with the actual mobile phones, you can, the SNR will be much, at this distance, which may be much greater than 0 dB. Okay, so of course, this is no practical conclusion, because this kind of schemes that we're proposing are not, are far from being implemented anywhere. But somehow it gives hope that you can still do better than multi-hop, and that it's worth looking at schemes that modify the physical layer of wireless network in order to achieve higher throughput. And that's the take-home message I want you to take. And another take-home message is an open problem. If you remember, if you noticed well, I addressed 3 problems: the case where there is neither space nor power limitation, the case where there is only power limitation, the case where there is only space limitation. So we were thinking, okay, now we have the whole picture. Actually, not at all. And when we were looking at this case, when now you are both limited in power and area, then what is the optimal thing to do? And here there is an open problem, which I think is quite interesting. We're working on it right now, and hopefully, I mean, if you have any ideas, they are most welcome. Okay, thank you very much for your attention.
Okay, questions?
How does the power scale in your scheme? Like,
How does the power, so the condition that we have here, right? Well, it depends on the area, right?
Okay.
So we need the power, we need
It will
the,
scale obviously like area, right?
yeah, so exactly, so we need quite high power in order to achieve what we promised. Yeah. If the power is, but as I said, when you decrease the power below this threshold, you come in the situation where there is both area and power limitation, and this is the.
So just wanted to know in your scheme like what.
Yes, yeah. So we need.
Do we have another question?
What's the technical difficulty in including in your analysis or in considering in your analysis random fading coefficients?
Actually, it's not a, this was not a, okay, so let me go back to square one. Including fading coefficients actually helps. So I'm taking this model because this was the model that was proposed by Massimo. And this is the model, the hard model to deal with. What we had originally as a fading model was an IID fading model. So each phase was independent and uniform And in this case, there is no area limitation. You don't see the area limitation problem. So you can have arbitrary throughput even when we're in a very small area, in the dense case, for example. But if you move to this model, which is more realistic, it's still random, right? Because the randomness in the phase is in the distance between the two nodes, but each is much less random than before, and that creates the limitation in the MIMO gain or the MIMO transmission that you have, and that's the difficulty, is to show that you can get still quite a decent number of independent bit streams in this case, and that was the last technical thing we did.
Okay.
So, I mean, there's still this pole there, which is essentially, I mean, so you have the far,
Yes.
this is a far field model. And
It is
so
a
when you would densify or anything like that, this pole creates sort of
Yeah, so
questions. So could you what
Yeah.
survives? What does survive when you remove this pole?
well, the thing is, in a dense case, in a dense network, so we had lots of argument about considering this model. So the thing, what would you replace the model with? You would replace with 1 plus R, for example. This is completely unrealistic in a dense case because that's it. So what we are arguing that this model, even though it has an infinity at 0, is still the right model to look at. It's the model. So I should mention something in our scheme. We are not at all using the fact, this artifact, that you have infinite gains at very short distance. Because in our scheme, we are only doing transmission on the long range, long-range transmission. So we are not, and even if we are doing short-range transmission, we are not taking advantage of the fact that we have this huge gain. And what we've been arguing is that actually this is the right model, because this is the model that shows that, you know, the important thing you want to have in a network when you have you're communicating to your nearest neighbor and you want to see the impact of interference to a node which is far away, you want to see that the ratio between these two is this 1 over r to the 1 over r, right? And if you move away from this model, you won't have this effect. And this is the most important effect, right? That's the thing that allows spatial radios in wireless networks, because there is this decay with power r over distance, with this decay of 1 over r with distance, and that's what allows to have many simultaneous local transmission in the network. And if you move away from this model, everything breaks down. So since this model is also coming from a reasonable, from Maxwell's equation, we think it's the right one to look at.
Okay, let me stop the questions here, but before we all leave, Francois has some final words. Let's thank Olivier again.